I'd like to thank the speakers for inviting us here today. There's actually a third person involved with this project, which is Ken Westra, who's sitting in the back as well. All three of us are going to be around, so you can talk to us if you like. I'd like to thank the speakers for inviting us, and this is a fairly new project that's been going on for less than a month. And so I'm going to change things around a little bit and talk about what we'd like to do more so than what we've actually done. And I do, of course, realize that I'm between you and lunch, so I'll try and keep it lively and brief. Okay, so to start off with, there's myself with Wilson Analytical, Ken Westra with Helmet Creek Technologies, and John with HJC. And we've had assistance from Neil and Brian Moore at ACAMP asking us whether it would be possible to develop rapid on-site oilseed seed chemical analysis. So first of all, just for the rest of the speakers, I've got a green laser pointer here as well, so as long as you don't mind using both hands, this one's probably a lot easier to see. So the problem is we'd like to be able to do chemical analysis. Okay, we'd like to be able to do chemical analysis, and it's very critical to do that when you're using oilseed products for things like biodiesel production. But the problem is it's currently very slow and expensive to do the type of detailed chemical analysis that you actually need to be useful. So the solution would be to develop a fast, portable, inexpensive, and effective system. So the way we're looking at doing that is we have a team of the three of us who are seasoned professionals in various areas that are needed to do this. But what we need is we need people to join with us and help us both to guide us with the definitions of the assay needs, because obviously if we don't get this right, it's not going to be of any use to anybody, and also to help us with the funding to develop the equipment and the prototypes. So a little bit of background. There are several oilseed sources that are used, including canola, flax, and hemp. But the important thing is that it's the oil's chemical profile that determines the suitability for nutritional and industrial applications. And of course, in most cases in the field or at point of sale, a lot of stuff that's looked at is just seed quality, not chemical analysis. So the canola consumption in Canada is mainly used for biodiesel for farm use. So the idea here is to have some of your canola production being recycled back into your own fuel use to cut down on fuel costs. And of course, as most people are aware, canola is used for food production. There's considerable growth in both of these areas. It's driven by both biodiesel and the food products. And this graph here shows the actual and the projected growth of the canola sales to the United States from Canada. And then you can see here the target here is over 2 million tons of oil per year. So what's the problem? Well, the problem is that we want rapid on-site oilseed for biodiesel or for other uses of the oilseeds, and rapid on-site chemical analysis is sorely lacking. And there's a good reason for that. The reason for that is that the things that you actually need to analyze for, such as cloud point, the chemical content or the extent of the reaction, biodiesel production, chlorophyll and things like that, are very difficult to analyze chemically. This is a complex organic matrix. So to do it properly, you use a full-size laboratory. And that's expensive and slow and therefore ineffective, because what you actually want is you actually want to have these parameters so that you can actually make process control decisions when you're trying to run your biodiesel plant, or you're trying to sell your oil, or you're trying to look to see when you're growing whether this particular field is going to provide a good yield of the chemical that you're growing the oil for. So what we need are analytical instruments and methods that are on site. They're rapid. They take minutes or possibly hours, but not days. And of course, they're cost effective, because there's no point in having a test and equipment that costs too much to actually be useful to the end users. So that's all fine. It's obvious to anybody who's looked at this problem that that's what we need to do. But the question is, how can we do this? And the way that we think this can be attacked is by using miniaturized chemical analysis. We've already seen some examples of this today in some of the earlier talks, and I'll sort of go over the same sort of thing. But the idea is you can directly inject small volumes of the oil. You will have analyses that are approximately the same quality as what you get off the large laboratory instrumentation, but 10 times faster because of the way the instrumentation is used. So we're typically trying to make the devices about bread box sized, and they have to be made very robust. So this will allow them to become effective for on-site real-time process analysis. So that's fine, but the question is, how do we think we can actually approach this? Because as I said earlier, if you don't actually get chemical analyses that tell you what you need to know, there's no point in doing this project. So what we've looked at so far is water content. The gold standard for water content is Carl Fisher titration, which I'll talk about a little bit in an upcoming slide. And however, we're also talking about using attenuated total reflection infrared, which I'm also going to talk about later on for the chemical analysis, and there's a possibility of using that as well for water measurements. Another thing that's important on the usefulness of the biodiesel and fuels and other things are cloud point tests and solids content. And we're looking at using optical and MEMS-based devices to actually test for that in the field situation. And of course, most of these things have a temperature component to them, and Alberta gets very cold, as everybody here realizes, so you have to be able in the field to simulate Alberta in the middle of January, and we're looking at using Peltier-cooled devices to do that. If you're talking specifically about biodiesel, you're converting it to make fatty acid methyl esters, and so you want to look at the extent of the reaction from the original starting material to the FAME content, and we're looking at doing that by ATR IR absorption. So what we're really looking for here is partnerships, and one of the partnerships that we need is, before we can develop any of this type of stuff, we have to start off with having the gold standard answers. So basically we need people who know what is useful in this area from the normal chemical analysis to give us the answers that we need. Typically the problem here is going to be that we don't need to analyze absolutely everything that's typically done to qualify a biodiesel. What we need to know with people, from people with the expertise, is what are the important points and how do those look chemically. So in other words, my tractor doesn't start and that's because of X, and we can test that by Y. And once we know what the answers are to that, then we'll be able to convert that into field analyses. So we welcome input from all who work in the field, especially those who can help us out with some of those questions. Okay, so I mentioned on the last slide how we can do this. Let me just show you what the starting point is. This is an example of a Carl Fisher titrator. It's an auto titrator. It does a very good job of measuring water content. It has very low interferences from other things. It just has one slight problem if you want to stick it on the back of a tailgate of a pickup truck. So this is the gold standard method for doing water analysis. We're looking at converting that to microfluidics. So the idea would be this would be a lab on a chip application, but basically it would be an auto titrator on a chip. So that's one thing that we're looking at and considering. The other picture up here is showing you a Peltier module, just to give you an idea on how small they are. These are magical things. You put power into them. One side of the ceramic gets hot, the other side gets cold. We have some experience with this in our groups of companies here, and that's our preliminary ideas for doing the cloud point testing. On the chemical analysis side, for the extent of reaction, and also for other people who are not interested in biodiesel but might be interested in the different chemical components in oil, what we're looking at is using Atr Infrared. And so let me just explain to you how this works, and then I'll tell you how we're planning on field hardening it. What you do is you take a crystal that has a high refractive index, and you can see the crystal is here. And what you do is you bounce infrared light into the end of the crystal, and the infrared light bounces through this infrared transparent crystal, and it comes back out and goes through a detector. And you say, okay, so what? So I've stuck some light through a crystal. How does that help me? Well, what isn't shown right here is because of quantum mechanical effects, a little bit of this infrared wave actually comes out into the space above the crystal. And so if you stick a sample in here that touches the surface of the crystal, you have a very short length infrared pass cell that is very robust. And you can change the sensitivity of the measurement by determining the number of bounces that you do inside of the crystal. So this is a multi-bounce crystal here, and in the picture over here on the side you can see this is a single bounce crystal. These crystals are made out of very hard materials. This one actually is diamond. You can also use germanium and silicon and other things depending on how you want to do the measurements. And the big advantage of this is the path length is fixed, cleaning is easy, and as you can see in the picture here, the sampling just depends on putting a drop on the surface here. And because the path length is fixed by the geometry of the experiment, you don't have to worry about how much sample you put on, how you do it and everything. You just put a drop on, run the experiment, then use alcohol or something to clean the surface off. And because these crystals are very hard and the rest of the unit is stainless steel, it's very field hardened and very easy to keep it going out in the field reproducibly. Okay, those are the macro instruments. There's also a lot of expertise in this area in going to micro. This is Microline here. This is their example of a microfluidics toolkit chip, which is based on glass. And so you've got a long separation channel here, and then you've got the analysis potential on the side. Now these types of chips and similar things like this have been used to commercialize other things. This is an example from Agilent here where you have a chip that's used to do DNA and RNA sequencing, and you take this chip, you stick it inside of this thing that looks like a tower computer, and you introduce your solution on, and the chip does everything that a large-scale chemical analysis setup would do. Some of you may be familiar with the point of use diagnostics tests such as ISAT here from Abbott. The same idea, there's a chip inside, you take a drop of blood from the patient, stick it on the end of the chip, drop the chip into the reader, and it does up to 8 different chemical analyses on the blood sample, doing blood gases and other things that people need to know in an immediate fashion for point of care. So what we're interested in doing is a similar type thing, but on the agricultural side. So who's our team? We have Ken Westra. I notice there's a bit of a trend here today. There seems to be a large population of Kens involved in this organization here. So you've got Ken Westra, who has over 26 years of experience in microfabrication and started up a large number of companies, and also has the advantage of coming from a farming background. His company is Helmet Creek Technologies, and as I mentioned, Ken is here today. There's John Crabtree, who, as he says, he wrote the slides here, so he's a city slicker but still a nice guy. He has over 20 years of experience in microfluidics and analytical chemistry development and product development. And then there's finally myself. I've got many years of experience in spectroscopy and product development. I noticed this when I put the slide in. Plant in this case does not mean a green thing with leaves. Plant in this case means an industrial refinery. So I've worked on analytical development and support for process control laboratories, and this is not very different from that type of situation. And actually, we also have a product at Wilson Analytical that is along the same lines, and in fact, I mentioned chlorophyll measurements. This product is actually capable of measuring chlorophyll directly. It was designed for the oil field. It's a ruggedized fluorimeter, and what it does is the first analyte that we're measuring with it are corrosion inhibitors for pipeline and gathering systems for the oil field. So that's the reason why it's so ruggedized. But obviously, if it's rugged enough that the oil field can't break it and they can operate it, it's very easy to move it over to an agricultural situation, because all of the same types of things that are required are the same for both applications. And by the way, if anybody's interested in working on moving their fluorescence assays from their laboratory applications out to the field, this is a general purpose fluorimeter that's specifically ruggedized and has LED-based high brightness excitation and full spectrometer detection. So we're also looking for partners to pursue working in other applications for our quad box technology. So here's our pitch. We'd like to build a product that will allow people to get higher revenue from their oilseed production and their biodiesel production, but we need guidance, because the trick here is going to be to figure out which chemical analyses are important for process control and how we can actually calibrate for those and vet them. And we also are seeking financial support from the agricultural sector to allow us to bring this project forward. And I'd like to acknowledge Neil and Brian Moore from ACAMP for bringing the opportunity to us. And here's the contact information for the three of us, and I'd be quite happy to answer any questions.